Have you ever looked at a graph and just known two lines were parallel? Well, today we're going to go way beyond just looking. We're diving into the algebra that actually proves it. Trust me, it's a core skill that's going to unlock a ton in math for you. Let's jump in.
You know, we see this idea everywhere. Just picture a set of railroad tracks stretching out to the horizon. They're on the exact same path, right? Running side by side, on, but they'll never ever cross. That simple picture, that's the heart of what it means to be parallel.
But here's the thing. In algebra, it looks parallel, just doesn't cut it. We need proof. So how do we prove it with 100% certainty just by looking at their equations? That's the puzzle we are going to solve right now.
And the answer, lucky for us, comes down to one really simple, super powerful idea. I like to call it the golden rule of slope. Seriously, if you only remember one thing from this whole explainer, make it this. And there it is. That's the secret sauce. Parallel lines have the exact same slope. In the world of algebra, saying two lines have the same direction really just means their slope, their steepness, their angle is perfectly, absolutely identical.
So let's break this down. You see our good old friend y equals mx plus b. For two lines to be parallel, two things have to be true. First, that m, the slope, has to be a perfect match. That's our golden rule. But, and this is just as important, look at the b, the y-intercept. That has to be different. I mean, think about it. If the y-intercept was also the same, they wouldn't just be parallel, they'd be the exact same line right on top of each other, right?
Okay, that's enough theory. The absolute best way to get this stuff down is to see it in action. So let's get our hands dirty and put this rule to the test with a few examples. All right, let's start with level 1, just basic identification. We've got two lines here. Line A is y equals 2x plus 1, and line B is y equals 2x minus 3. So, based on what we just learned, what do you think? Are they parallel?
You got it. Yes, they absolutely are. The m in both equations, the number right next to the x, is a 2. Their slopes are identical. And see how that works on the graph? A slope of 2 means they both go up 2 for every one they go over. Same slope, different starting points on the y-axis. That's a textbook case of parallel lines.
Okay, time to level up. Now instead of just finding parallel lines, we're going to build one ourselves. Here's our mission. We need to create a line that's parallel to y equals 3x minus 5, but it has to go through one very specific point, 1, 4. So where do we even start?
It's actually a pretty simple two-step process. Step 1, and this is the fun part, we steal the slope. The original line's slope is 3, right? So for our new line to be parallel, its slope has to be 3. Easy enough. Step 2, we grab a handy tool called the point slope formula. All we do is plug in our stolen slope of 3 and the point we were given, 1, 4, and boom, we have the equation for our brand new parallel line.
All right, get ready for level 3. This is where things get a little tricky and where a lot of people make a simple mistake. You see this equation, 2x plus y equals 7, and it is so tempting to just look at that 2 next to the x and say, aha, the slope is 2. But is it really?
No way! It's a classic algebra trap. Remember our rule? We can only truly identify the slope when the equation is in that beautiful y equals mx plus b format. And this one? Well, it's not. That 2 is a disguise.
And this is why the number one rule for this level is you have got to solve for y first. You have to get y all by itself on one side of the equal sign. So we subtract 2x from both sides, and that rearranges the equation into the form we need. Y equals negative 2x plus 7. And just like that, the true slope is revealed. It wasn't 2 at all. It's negative 2.
You know, that last example is the perfect lead-in to our next section. Let's talk about a couple of those really common traps so you can see them coming a mile away and never fall for them.
So this is the first trap, the one we literally just saw in action. It's so easy to just get in the habit of thinking that whatever number is glued to the x is your slope. But, as we just learned, that's not always true. It's only true when the equation is already solved for y. For anything else like this example here, your very first job, no matter what, is to do the algebra to get that y all alone. Only then will you see the real slope.
And here's the second big mistake people make. When you're creating a new parallel line, it's easy to get into this copy-paste mode. You steal the slope, and then you accidentally just grab the old y-intercept too.
But you gotta be careful. Remember, you're a slope thief. Your one and only job is to steal the slope. Leave everything else behind. The new y-intercept, that b value, isn't copied. It's brand new. and it's calculated based on that specific point your new line has to go through.
So we've gone through the math, we've dodged the traps, but you might still be thinking, okay, but why does this actually matter? When am I ever going to use this? Well, let's connect it to the real world, because I promise parallel lines are absolutely everywhere.
I mean, just think about construction. The beams in a roof have to be parallel, with the same slope, to make sure the building is strong and stable. Or when you're driving, the lanes on the highway are all designed as parallel lines to keep traffic flowing safely. It even shows up in video games. When a character moves forward, the game's code is calculating a path that is parallel to the direction you're pointing. It's like the hidden language that shapes our world.
So, we've totally nailed it. The golden rule, parallel lines have the same slope. Which leads to one last interesting question. If identical slopes create lines that never ever touch, what kind of special relationship do the slopes have for lines that meet at a perfect 90-degree angle? That's a good question for next time. Thanks for hanging out for this explainer.